thank you very much for the invitation. I'm really glad to share this project. So our whole team is at ETH. Susie Rao is rather at the computer science end of things. And Peter and me, we're economists. And we are interested in the vertical urban development. So maybe I switch right to here. So the core idea of this project is that for the first time right now, or over the last 30 years, I might say, this urban industrial transformation was actually seen from space. So this urban transformation happened before, right? I mean, in Europe, maybe 150 years ago, the Asian tigers, maybe 50 years ago. But now it's different, that there is actually data, and we can actually see this year by year differences. And we plan on making this available for urban economics. All right. So maybe to give you a little bit of context, so we're talking about China. I'm located in Wuhan right now, by the way. We had this communist era where basically this farmer lifestyle and this rural lifestyle was really idealized. And then in the 80s came this change, and with that came liberalization, came industrialization, and with that urbanization as well. So we see this very nicely here. In the 1980s, we had like not even 20% urbanization rate, and this went up to 2/3 right now. Or as Bill Gates apparently puts it, China used more concrete in 3 years than the US did in the whole last century. So we have this urbanization on this massive scale in China happening, and we can actually see it year by year. Two more building blocks of that, other than the satellite resources that are available right now, is urban economics made huge steps forward, and finally kind of came away from this idea of just having one central CBD point and then concentric circles around that. So we can do actually much more complex analysis today with recent development within the last 10 years or so, or even just 5 years. And then on top of that, well, obviously algorithms got much better. So we have a whole literature now that does 3D reconstruction from satellite imagery. But often this is rather in the computer science or in the remote sensing literature, and people are not so much interested in large-scale in large-scale models. They're rather interested in just showing the methods and improving these. And we as economists have this interest in having long panel data on a large scale. So this is really what we bring new with this paper. So let's jump in. So what we use, at least for this paper, this project has made quite some advances since, but so for this paper, we use the Sentinel-1 and 2. This is 2 different satellite constellations of the European Space Agency. They have a resolution of 10 meters, so it's a pixel, 10 by 10 meters, roughly, a bit less. And so Sentinel-1 is a radar. You see this to the right, and Sentinel-1 is a natural color plus infrared satellite. Right, and then we need reference data. So we want to train a model. This comes from AMAP, which is or Gauda D2, which is the Chinese equivalent of Google Maps. And it's crowdsourced, scraped. It's widely used for in remote sensing in China, but it's not completely clear where it comes from. So we had to actually manually check which year it has missing data. So it has some issues, but it covers 77 cities, and that's Chinese cities. So it's a huge amount of data. With manually and with certain techniques, we bring this down to 40 cities that we actually trust the data is all right. And then we translate this into this 10-meter grid of Sentinel. And then the actual core engine of that whole thing is a relatively standard UNet algorithm. It's a ResNet 34 with an encoder, decoders, Okay, I'm talking to economists here. So what is maybe important is that the main change we make is that we have two prediction heads. So we predict a height regression, and at the same time, we predict a footprint. So for each pixel, we decide, is it a building or is it no building? And also we predict a regression. And then in the end, we just mask out the regression with our footprints. We do the whole different, we test a lot of different architectures in the paper. If you're interested in that, you can look at that. Important is we have these 40 cities that we train with. We leave out Shenzhen. This is our test set. And all the results you're going to see are only for Shenzhen. But the idea, obviously, is to employ this model on a large scale, on basically, so Sentinel is available everywhere in China. So theoretically, if we would have the servers to do that, we could just run this over everything in the country. So we can really work on large scales and also on different years. Right, so let's go to the results. So maybe I just let you have a look on this for a moment. So we have the natural color image to the left, and then in the middle, this is the reference data. So it's the ground truth, but we call it reference data because we don't fully trust it. And then to the right is our prediction. So if you look at this, I think a few things jump out right away. We seem to get the structure quite right. High buildings are high, low buildings are low, and we see clearly the streets and all of that. What is quite obvious is that if there are small buildings and they're near together, they kind of lump together into one big structure. This has a lot to do with the resolution that is just given by the satellite. Yeah, I can talk about this in the end. We employ different satellite imagery right now. And the other thing I think that is important to remark is that we don't see any yellow in our prediction model or in our prediction, because we don't predict the high buildings really high. So to really bring this point home, we can see here the distributions. So this is the pixel-wise distribution of height for the reference data, and then for our prediction. So the distribution is very different. We don't really get these high buildings to the height where they actually should be. But then there's also good news. If we actually look at this in a, so here it's also a logarithm. So we have on the x-axis, we have the reference data height, and on the y-axis, we have the prediction. we clearly see how it's actually not exactly the 45-degree line. It's a bit below, but we have a striking regression, right? So it seems that we actually get the relative height quite well. So we predict high buildings high and low buildings low. It's just that they're systematically too low. And this is just a bit a different view on the same topic. So this is the R squared in different aggregation levels. So the amount of variation in height that we can actually explain with our prediction. And then if we look at the 10-meter resolution, this is only 30%, but it increases drastically if we aggregate this slightly. So up to the point where in a 2 kilometer to 2 kilometer pixel, so on the neighborhood scale, we basically see the whole variation. So this is just to enforce once more that a lot is explained. It's just some of it is predicted too low. Right, and then so in the next step, we compare this to nightlight data. The idea is that it became quite normal to use nightlight data in economics, and especially spatial economics and urban economics, to approximate all kinds of things. For example, GDP or population, or things like more abstract density, or for example, to see how centralized or decentralized the place is. So so we go ahead and compare this actually to nightlight data. We see this is the whole city of Shenzhen. We see our reference data on the top left, and then the prediction on the top right, and then the nightlight reflectance on the lower left. This is all in a 100-meter scale, so it's slightly aggregated just to match the nightlight, because this is the best resolution we could get for the nightlight. I think it's very obvious that the overall structure is relatively similar. So then we look at the difference. So and at the top we see the difference between the prediction and the reference data. So red means that our prediction is higher than the reference data, and the blue purple means that the reference data is higher than our prediction. So we can clearly see that our model sees a lot of buildings that we don't have in the reference data, especially in the top, so at the edge of the city, as well as in the lower parts, which is actually already Hong Kong, and is therefore also not in our reference data. And then we also see, which agrees again with the point I made before, that actually the height is everywhere but too low. But now to the comparison with the nightlight data. So we clearly see here, again, blue means the nightlight data overshoots our prediction. And then, so we added here a couple of interesting places, such as ports and airports, which are, well, clearly the nightlight is very strong there, while we predict basically no buildings or very few. And also, and I think that's the main point here, is that highways are very, very visible in the nightlight data, and not in our data, obviously. So I think the point I want to make here is that nightlight heavily over focuses on infrastructure in general, and on streets specifically. So if we, and I mean, that might be for some things a good proxy, but it's not actually a good proxy if we want to look at inner city structures. Right. Then I just tell you about the where we want to go with this project. So obviously we have to work on this height regression. A lot is done already. All the things here in the bracket are already implemented. So we experimented with transformers, a different deep learning algorithm, then with gradient loss, and also we did a lot of augmentation of the images, which all contributes to improve that to some extent. Then we want to go further back. So Sentinel is a great resource, but it has the major drawback that Sentinel-2 only went to space in 2017. And for us, we really want to go back to 2000 to really see this whole development of these Chinese cities. And therefore, we employ the planet constellations now. That should bring us back to 2009, roughly. And we're in parallel working on methods to go even further back, but that with Landsat. So this is much lower resolution, and we will have to see what we can work out there. On top, I mean, you haven't really seen the scale because I haven't shown any other cities other than our test set, but we really want to do this on a large scale. So we want to be able to really cover the 60% urban population in China, and bring this back into economic models. So that brings me to the economic side of things. We are currently working on 2 projects, and we have more in the pipeline. So obviously we do kind of classical Rosen hedonic housing pricing for traffic networks. So the idea is to see the development of high-speed rail, as well as the subway systems over the years, and really see that in a panel structure. And the other thing we're working on is local exposure to trade shocks. So can we identify densification processes based on positive trade shocks? So these are 2 ideas we're already working on, but we think the application can be much further reaching.
Okay.
Right, that's actually it.
Okay, thanks a lot, Sebastiano, for this rich and very, let's say, insightful presentation, which shows some first insight. Of course, there is still a lot of room for improvement, but still you managed to do, let's say, a big step towards having the 3rd dimension, which is, of course, key if one day we want to have an idea not only of the surfaces, but also the volumes of construction, which could be very useful, including, for example, for the national accounts. Why not using some gross fixed capital formation with this kind of techniques, including why not for, let's say, developed countries? Perhaps if this is, let's say, the technology is reliable enough, perhaps we could even use it to, let's say, construct GFCF in real time, perhaps even infra quarterly basis. That could be an interesting prospect, including for other countries in developed countries. So, okay, thanks a lot. Are there some questions on this presentation? There will be 2 other presentations from CounCube and the OECD on satellite data. So I guess that at least is going to generate some things for thought. And indeed, I guess that it's only a first step, and that you will explain the thing. So your next step is on China. You're going to try to cover more extensively China. But I guess that some other countries, perhaps that could be smaller, would also be interesting, including in emerging countries, because I guess that the size of China, which is 10 million square kilometers, perhaps makes the thing a little bit more difficult. And the fact that you have high densities on the east coast, I guess, also makes the things difficult because, as you said, in very dense areas, the calculations are more difficult. So I guess that perhaps you could also envisage to focus on other countries with perhaps less dense areas and perhaps smaller surfaces. What could be the other countries outside China? Do you have some plans for that?
Not really. So the great thing about China is that it's a huge country with a very similar building.
Yeah.
It's a very similar architecture.
Yeah, okay, I see the point.
And the generalization of this model is probably not so great. So we would need for every context, we would need new reference data to train the model with.
Of course, yeah.
So I think our focus, but the great thing is China with its size actually only looking at, I don't know, the 10 big cities in China is already gives you amount of data to work with as if you would work with I don't know, all European countries or so. So and I think that's actually a huge upside of it, right? That we don't have to adjust to so many different contexts.
No, indeed. Okay. Okay, and did you have some contacts with the people in charge of statistics in China, even including in China, because this could be also interesting for them?
So I'm right now sitting in Wuhan, and we're working on a collaboration with the Remote Sensing Institute here.
Okay.
We haven't really had any contact with city or country officials, but I think. So for us, this is really just the first step. It's this very technical thing, and we're really interested in the economics that lie behind that.
Of course. Okay, but I guess also for World Bank, this could be interesting because, of course, China is a huge part of the emerging world GDP and GFCF. So, and as you said, and Benjamin is going to recall it, cement industry is a huge industry, and in China, it's the biggest producer of cement in the world. So indeed, focusing on this country is key for the world construction. Okay, very interesting. I guess that could give many ideas for most participants. Other questions before we switch to the conference for the presentation from Concube that I think will be quite complementary from yours? No? Okay. But thanks a lot, Sebastiano. That was very interesting. I was very curious about having your presentation, which was quite new for me. Having this dimension was very, very original and very interesting. So thanks a lot. And of course, we can keep in touch with you for the future.